Well, let's get things started here. Next section in your chemistry text is looking at the idea of covalent bonding and how it's associated with the compounds that we see. So we just finished, or maybe not finished, but we were looking at ionic compounds today in class and yesterday in lecture. So covalent bonds are different in the sense that rather than like ionic bonds where one gains an electron, one loses, covalent bonds share the electrons. So the electrons spend time near the nucleus of one atom and then spend time near the nucleus of another atom. And so there's a number of electrostatic interactions going on, meaning, so you've got like the positive charges of the nuclei, which repulse one another, but it's the nuclei that actually attract the electrons from both the electrons within their atom and then the electrons of another atom, thus the sharing of electrons. And then there's repulsion between all the electrons involved in the bond, in the covalent bond. So you've got these three types: attractions between electrons and the nuclei, repulsions between the electrons, and repulsions between the nuclei. So my hope for this section of the textbook will be that by the end you'll be able to identify the difference between an ionic and a covalent bond, that you'll be able to explain and apply the differences between polar and non-polar bonds. What's the difference and why is that important? How does it come out to play in chemistry? And you'll be able to calculate and apply the dipole moment of a covalent bond, as well as understand the continuum of the bonding types and the properties associated with them. So a polar covalent bond, so you can have atoms that share electrons evenly, and then you can have atoms where they don't share the electrons evenly. And when they don't share evenly, then you get a polar covalent bond. So here we have the same. Though atoms often form compounds by sharing electrons, the electrons are not always shared equally. So our example here, two fluorine atoms are going to share the electrons equally because they're identical atoms. So one doesn't have a stronger electron affinity than the other, where hydrogen bonded with fluorine does. The electron affinity, or the desire for one more electron, is much greater for fluorine versus hydrogen, so the electrons spend more time around the fluorine. So fluorine pulls harder on the electrons it shares with the hydrogen than hydrogen does. Therefore, the fluorine end of the molecule has more electron density than the hydrogen end. And that makes it so that the fluorine end of the bond is the more negative end of the bond because the electrons spend more time in that portion of the bond. And the hydrogen end is more negative or more positive because the shared electrons spend less time around that nucleus. The best way to calculate or to determine the polarity or the difference for different atoms is to use electronegativity values and to then calculate what the relationship was going to be. Now you notice the trend, so there's a trend in electronegativities. So fluorine is the most or has the highest electronegativity value, and then everything else is kind of based off of that. So the lowest electronegativity, excuse me, is down there at the bottom of the alkali metals. So knowing this trend is actually a decent way of predicting how polar a bond is going to be, at least comparing it. So on the periodic table, electronegativity increases as you go from left to right across a row and from bottom to the top of a column. Okay, so it increases as you go up a column. And then there's obviously, looking at the diagram, there's some exceptions there in the transition metal area. Okay, so a polar covalent bond, when two atoms share electrons unequally, a bond dipole results. Okay, so a dipole, and we've got another equation here. This one is related to kind of the dipole moment, or the kind of how polar is this bond. So it's produced by two equal but opposite charges separated by a distance of r. And it's calculated by using that equation, which we'll practice in class tomorrow. But so what this gives us, so when you look at so you've got electronegativity difference values as well as dipole moment values. And the greater the difference in electronegativity, the more polar is the bond. So hydrogen fluoride has a greater electronegativity difference and therefore is the most polar, has the greatest dipole. And then going to hydrogen iodide, you have the lower electronegativity, and obviously the size of those halogens are getting larger as well, and so there's more shielding of the nucleus from that outer electron, and so the electronegativity pull, the pull of the nucleus for that additional electron is going to be a bit weaker. So we'll talk a bit more about this in class, look at some problems, and I will see you tomorrow.